So we will talk about some key aspects of gravitational waves that will be necessary for doing cosmology. Then I'll be talking about a bit about Bayesian parameter estimation. I'll be abbreviating every now and then. PE here stands for parameter estimation. I'll try to talk about selection effects if I have time. And I'm going to talk about some projection for the future. And some open questions. So this will be the topic of the first lecture, and these will be the topics of the second and third lecture. So let us begin with a plot that all of you have seen. This is not some plot that's too complicated that I cannot draw on the board. Let us draw this figure of the gravitational waveform. We'll keep this interactive, so let's begin with the question. What do we see in this waveform, this figure that has become famous, that we do not see in astronomical observations? What is different in this figure that we do not usually see in electromagnetic astronomy? Any answers? Sorry? A time variation, good. What else? Time variation we do see in transient astronomy. Amplitude variation, frequency modulation. So the most important thing is we see an amplitude and a phase. This phase is something that we are usually not sensitive to in electromagnetic astronomy. Not in all cases, but in most cases, we observe only the intensity, while here we are sensitive independently to the amplitude and the phase. It's going to turn out that this is going to be very, very important for the kind of cosmology that I'm going to talk about. So we are able to track the phase evolution, as a result of which we are able to search for certain modeled signals. So this is only one kind of sources that we are looking at. I must have kept the pointer somewhere. This is a slide from Samaya, who I'm replacing. This traces out some of the differences between optical astronomy and gravitational wave astronomy. One of the most important things is because we are sensitive to phase, we are looking for coherent sources. While in optical astronomy, we usually look for incoherent sources from incoherent signals from different parts of the source. So we see only the intensity and not the spectrum. Another important thing is we are directly sensitive to the amplitude, and the amplitude is something that falls off as 1 over r. While in optical astronomy we are sensitive to the intensity, amplitude falls off as 1 over r, while the intensity falls off as 1 over r square. It falls off a lot faster. This means that if I build an electromagnetic detector that is twice as sensitive, then I can look square root of 2 times farther. Well, if I build a gravitational wave detector that is twice as sensitive, we go not just square root of 2 times farther, but twice as far. So a small improvement in the sensitivity takes us much farther away for gravitational wave detections. Going further with the overview, these are not all the kinds of sources that we see, but there are different kinds of sources. So we can draw some kind of a chart here. And instead of weak and strong, what I'll call here is something that are transients. So transients are things that appear only for a short time, and some things that are long duration or a background. And we can also have sources that we can model and sources that are unmodeled. Of course, we have these compact binary coalescences, which we already talked about, which show signatures like this. They are reasonably strong transients. They stay only for a short duration. For how long can someone fill in? Sorry? From a few milliseconds, let's say about 100 milliseconds, what we observe in the current sensitivity band, to maybe a few minutes. There can also be transients that we cannot really model. These are things like supernova explosions. So it would just be some kind of an unmodeled burst signal. It will be loud. We'll be able to see it above the noise, but it would be difficult to exactly expect what kind of a signal from any underlying physics. The long duration signals are some continuous signals, almost sinusoidal, with some modulation that comes from the rotation of the Earth, or revolution of the Earth. And what can give out a continuous signal like this? If you have a neutron star that has some kind of a mountain, some kind of a small bump on top of it, and if this neutron star is spinning really very fast, then there's a change in quadrupole moment. And as you probably know, a change in quadrupole moment generates gravitational waves. We are able to see this at twice the frequency of rotation of the neutron star, and that we observe as continuous signals. If you have any questions, then you should stop me and ask me. I'm not going to give a very thorough overview of gravitational waves because you might have heard other lectures, and because I won't have time to go into things in gory detail. So I'm going to just mention some key aspects, and feel free to ask me to fill in if you find that I'm missing something that you do not understand. Then there's the unmodeled stochastic background. Unlike all these other sources which are coherent, where we are very sensitive to the phase, here we have lost the phase information because of superposition from a large number of sources. So this is the stochastic background. And the stochastic background can be the primordial background, which is very, very important in cosmology, and also the background from all kinds of other sources that are happening later on. So the primordial background is very difficult to observe, at least with the current and the near upcoming detections. What we would expect to see before that is the stochastic background that comes from the superposition of all kinds of other sources like CBCs, supernova explosions, continuous waves, and this is also something that's very important in cosmology, but we are going to focus mainly on this sector, CBCs, and we will talk about how to do cosmology with compact binary coalescences. Yes. From the stochastic background, we can get the power law. We can get the power law, and these sources like CBCs will give a certain power law, while the primordial spectrum will have a different power law, which is going to have a much lower amplitude. But yes, the frequency dependence of the expected amplitude, expected intensity. Answers your question? So that's essentially the only information. The power spectrum. How strong is the signal at a certain frequency bin? Okay. I'll very quickly mention some aspects of modeling, again, without going into gory detail. So, this waveform that I keep on drawing, this waveform has 3 distinct parts. The early part we call the inspiral. This part we call the merger, and this late part we call the ring down. The inspiral waveform, we can calculate the inspiral waveform using something called post-Newtonian expansion. For the merger, analytic calculations fail. We really need numerical relativity to calculate the merger. And for ring down, we can do some kind of a black hole perturbation theory. But we still need some fitting from numerical relativity. And all this can be done if we know some parameters of the source, some properties of the source. What are the properties over there? The masses, the 2 masses of the components. What else? The spins of the components. Usually we talk about spins in some dimensionless units where they're divided out by the appropriate power of the mass. And this is all there is for black holes. This is because the most astrophysical black holes are not expected to be charged, and if they're not charged, then we expect them to be described only by their mass and spin. This is something called the no-hair theorem. And due to this, there are only 6 parameters for these 6 initial parameters for these black hole sources. If they're neutron stars, then what happens? There can be many additional parameters that come in because of the matter in the neutron star. But to the leading order, what is important for gravitational waves is the fact that neutron stars, in binaries, they get tidally deformed. One neutron star gets deformed in the presence of the other. And because of this deformation, there is an imprint on the gravitational waveform. Yes. I made a mistake. 2 plus 6 is 8. Thanks for pointing this out. Not 6, but 8 parameters. So this is 2 masses, 3 spins here, 3 spins over there. Other questions? Yes. The astrophysical black holes are expected to be reasonably neutral. The astrophysical black holes are not expected to be very highly charged. So for all practical purposes, we can neglect the charge of astrophysical black holes. There is something else that I did not talk about that could be important here. The eight parameters are the mass of the first black hole, 3 spin components of the first black hole, X component, Y component, Z component. Similarly, the mass of the second black hole, 3 spin components, X, Y, and Z of the second black hole. No, all the black holes that we are talking about are classical black holes. So the spins are classical. And for black holes, there's also a constraint in the dimensionless units in which we are talking about. The total spin in these dimensionless units are less than 1. So if you write in terms of angular momentum, then it would be j over m square, but we're using dimensionless units here. And there's a name for this. There's a name for this theorem. So what's the name for this theorem? Does anyone know? What would happen if this dimensionless spin were greater than 1? We would get something called what kind of a singularity? Naked singularity, exactly. So that the spin is less than 1 in this dimensionless units is something called the cosmic censorship. Neutron stars, as I said, there are many parameters describing the matter within the neutron star. The most important parameter is something called the tidal deformability parameter, which tells us how much a neutron star deforms in the tidal field of the other neutron star. And these tidal deformability parameters, or simply tidal parameters, lambda, also then lambda 1 and lambda 2 for each of the 2 neutron stars, they also enter the set of parameters, making it at least 10 rather than 8 parameters. This is a simplification. This is a huge simplification. The physics of neutron stars is complex, but this is the minimal way in which we can introduce some parameters for neutron stars. Yes. The tidal parameters of the neutron stars, they are expected to depend on something called the neutron star equation of state. And the equation of state of the neutron star predicts a relationship between the mass and the radius. And once a neutron star becomes big, it also becomes kind of easily deformable. So that governs the how much the tidal deformability is. This is a rough answer without going into the details. I can give you references after the talk if you're more interested. Other questions? Okay. So, quick question. Is it true that for neutron stars, is it true that for neutron stars, what kind of dimensional spins do we expect for neutron stars? 0.5, much less than that, much greater than that? Dimensionless spin is angular momentum over the square of the mass. And this is dimensionless because we are working in, I should have mentioned earlier, we will work in C equal to 1, G equal to 1 units. So, any answers? Do we expect any? What kind of dimensional spins do we expect for neutron stars? The answer is it can be arbitrarily high. There's no censorship conjecture for neutron stars. So many pulsars that we observe have this dimensional spin that are much higher, of the order of 100 or so. But for these neutron stars in binaries, we do expect them to be reasonably slowly spinning. Okay. I've talked about the physics of neutron stars. One important thing is for the waveform that we showed earlier is a binary black hole waveform. For a neutron star, we do not really know after the inspiral what happens exactly. The numerical relativity here also becomes very complicated because of the matter in the system. And we get, there's the inspiral, then there's the merger, and there's some kind of a post-merger behavior here, which is rather complicated. And again, one has to rely on numerical relativity, and these numerical relativity simulations are still in a rather rudimentary stage. Okay, going on with parameters, there are two polarizations for gravitational waves. You have probably heard, and it's easy to write. It's useful to write them out as a plus component and as a cross component. To the leading order, this plus component goes as is this readable or barely readable or not at all? Sorry, there should be sign off. Okay, so the important things here are this leading dependence on the total mass. Here I should define m as the total mass and eta as something called the symmetric mass ratio. Yes, 1 plus cos square. Iota here is the inclination angle. So this inclination angle tells us how the plane of the binary is rotated with respect to us. So if we have a binary like this, and this is the direction of the angular momentum, then if you're looking, if the gravitational wave is being emitted in this direction, then this angle is the inclination angle. Phi over there is the orbital phase. And the other things like the frequency of the gravitational wave that can actually be obtained from the other parameters. So this is not really a free parameter. Is there any other parameter that I haven't described yet? The d. What is d? The distance of the source. And a very important thing to note here is this is quite expected, that the amplitude is going to fall off as 1 over distance, but this is also going to be important for the cosmology that we are going to do. It's incomplete to talk about the polarizations unless I also talk about how the polarizations affect the actual measurement. So what we measure is the strain in what we measure is something called strain. What is strain? Strain is the relative stretching as the gravitational wave passes through the detector. And the detector strain, which I will call h of t, depends on what the detector actually is like. And this detector now is characterized by something called antenna pattern function or beam pattern function for the particular detector. So h of t is f plus of various angles times h plus f cross, which is also a function of various angles, times h cross. I still have to write out the various angles. Now, since we are running out of characters, I'm going to introduce a phi here, which is not the same as the other phi. So maybe I'll write it as a different kind of phi. Let's see what kind of phi I put in there. Fine. Theta phi psi. This is minus 1 plus cosine squared theta, cosine 2 phi, cosine 2 psi, minus cosine theta, sine 2 phi, sine 2 psi, while f cross as a function of these angles, all these phi's are the other phi. Theta phi psi is plus 1 plus, this is a 1 plus cosine squared theta, 1 plus cosine squared theta, cosine 2 phi, sine 2 psi, minus cosine theta, sine 2 phi, cosine 2 psi. So here theta and phi are just the theta and phi for the spherical coordinate system, and psi is something called the polarization angle. And this polarization angle characterizes how much h plus we have over h cross. So if the polarization angle is 0, for example, then you see that if the polarization angle is 0, then there's a sine 2 phi here, sine 2 psi here. You get only this term. If the polarization angle is 0, then you get contribution only from the h plus. The other term gives you 0 contribution. If the polarization angle is if the polarization angle is pi over 4, then the other term cosine 2, then the other term vanishes, cosine 2 psi. So this entire term vanishes, this vanishes, and this vanishes. So the entire contribution comes from the cross component. Fine. And this 2 psi indicates that these are again, as opposed to X and a Y polarization, these are plus and cross polarizations that are rotated by 45 degrees with respect to each other and not 90 degrees. Okay. 2 more things. Since I introduced a theta and a phi, these theta and a phi which describe the orientation of the source with respect to the detector are usually, it's more convenient, instead of talking about theta and psi, to talk about positions in the sky of the object. So these theta and this other phi can be mapped to the right ascension and the declination of the source, the sky localization and declination of the source. And it is not true that theta is alpha, phi is delta. There's some spherical transformation that's involved that can be worked out that depends on how the interferometer is located with respect to the sky at that certain instant of time. Let's count the total number of parameters that we have now. How many do we have now? We had, let's talk about black holes first. Let's forget the tidal parameters. We had these 8 intrinsic masses and spins. Then these are no new parameters. These just came along from the masses. We introduced 2 parameters here, the distance and the inclination, and also the overall phase. So there are 3 parameters here. And how many parameters do we have over here? RA, deck, so the 2 sky localizations, and the polarization angle, 3 more parameters, 3 and 3, 6, and 8, 14. We are missing one other parameter, and that is the, yes. That comes, FGW as a function of time comes from the modeling of the waveform. So that's not really a free parameter. It depends on the masses and the spins and when exactly the merger is going to occur. And since I mentioned when exactly the merger is going to occur, there's a 4th parameter here, the time at which the merger occurs, time of coalescence. And there is one other parameter, so that makes it 15 parameters for binary black holes, and at least 17 parameters to describe a binary neutron star system. Questions? Did I go too fast? Did I go too slow? Yes. The orbital phase is a function of time. So here 2 useful parameters are the phase at a certain time. So one can talk about the phase at the time of coalescence, if coalescence is well defined. For example, for a binary black hole, the coalescence can be well defined. Or one can talk about the orbital phase at a certain frequency. One can say what's the orbital phase at 200 hertz, or what's the orbital phase at 10 hertz. So we usually talk about orbital phase at coalescence. If you know the orbital phase at 200 hertz, then you can extrapolate what the orbital phase is going to be at the time of coalescence. And again, these are 2 parameters that kind of go hand in hand. Yes. At least 17. So then for the black hole, what's going to change? Are any of the extrinsic parameters are any of the angles going to become different? No. No, this part is going to stay the same. Are any of these parameters, distance, inclination, orbital phase, time of coalescence, going to change? No. What's going to happen in this sector? There's going to be only one tidal parameter. So there are going to be at least not 15, but at least 16 parameters. Other questions? Those functions are very specific to the detector. So what I didn't mention here is that these functions that I wrote down is for an interferometric detector for which the arms are at right angles to each other. And then this These are for an interferometric detector for which the arms are at right angles to each other. I'll try to draw it in some way. Let's say this one arm is along the x direction, another arm is along the y direction. This is the interferometric detector. Then these beam pattern functions depend on this is the theta angle, and the phi angle is the angle along the xy plane. Then I'll try to, I should have put this in on my presentation already, but I do not have it now. I'll try to put it in by the end of the day and also show you what these beam pattern functions look like for these interferometric detectors. If you change the technique of detection, then these functions are going to change. Other than one common other interferometric detector, that is not at right angles is this triangular configuration for a future detector called the Einstein telescope. If you have a triangular configuration, then what happens is you just get a factor of this angle, you get factors of trigonometric functions of this angle, so cosine pi over 3 and sine pi over 3, multiplying each of these two terms. Other questions? If not, let's see what I have in my slides. I already have a list of, this is something that I have already talked about, the parameters that are out there. Now we are getting to something interesting. I mentioned that for gravitational waves, we are sensitive to both the amplitude and the phase, and I also mentioned that this is going to be very important to us. How so? If we now want to measure these various parameters from the gravitational wave data, it turns out that just from the phase, we can measure the masses quite well. Okay, the phase evolution depends on the masses of the system. From the phase, we are able to determine the mass quite well. So phase already gives us various parameters of the system. Including masses, while now we can take these parameters that we have obtained from the phase and plug them back into the amplitude. And what's the dependence of the amplitude here? The amplitude depends, the amplitude to the leading order goes as the total mass, function of some angles, over distance. So I've already obtained, there are connections to this, but to the leading order, this is a dependence. I can take these parameters, including the mass, put them in, and it's important here that the distance does not really enter the phase. The distance enters only the amplitude. So let's let me take a step backwards and tell you what are the parameters that enter the phase and what are the parameters that do not enter the phase. All these intrinsic parameters over here, 8 or 10 or 9, whatever number you have, these govern. So let's distinguish between the intrinsic parameters. Intrinsic parameters are the parameters that are properties of the binary itself. So these things that are properties of the binary itself, they enter the phasing, because you can model the phase evolution of the binary with these parameters. The other parameters, the extrinsic parameters, they are not parameters of the binary itself, but they are rather a function of how we are located with respect to the binary. So that would be the various angles and the distance, especially the two angles in the sky and the distance, and things like the polarization and at what time the detection occurs. So these are the extrinsic parameters. These extrinsic parameters do not directly enter the phase. Some of them enter as angles in the beam pattern. Some of them enter as angles between the two polarizations. So from the phase, we can obtain these intrinsic parameters, and that includes the masses. We can take the mass, plug it back into the amplitude, and this now tells me the distance. We are able to measure amplitude independently, so we are able to measure distance directly to this source. We are able to measure distance independent of any kind of a distance ladder. While in electromagnetic observations, we need a distance ladder to go and measure distance. So gravitational waves provide a direct measurement of the distance independent of any distance ladder. Good. I'll just mention a few things that are going to be useful for us later on, but not to, yes, question. Yes. What are the tidal parameters and why? Why do I denote by lambda is something that I do not know, that I do not have an answer to. But these tidal parameters, they tell us how, they tell us if we have a field, if we have a tidal, okay. What's tidal effect? What's a tidal field? A tidal field is, do you know, or you have a basic idea, right? So if you come close to a heavy object, then the nearby, essentially the two nearby geodesics have the Roche lobe. It's not directly. So the Roche lobe is the region around the neutron star, which it's not very directly related. So these tidal deformability parameters are something like, if you have if this is the tidal deformation field, then the quadrupole deformation, is proportional to the tidal gravitational field. And here I wrote a capital lambda because, again, between the capital lambda and the small lambda, there's some scaling, and now I'm forgetting. There's a mass over radius to the fifth, which way, whether it's +5 or -5, I'm forgetting right now, but we can easily look up and see how this lambda maps to the dimensionless lambda. I think small lambda is defined as capital lambda divided by m over r to the 5, or it could be minus 5 over here. Other questions? So this is a measurement. Let me see if I can say things better. So with gravitational wave observations alone, we are able to measure the distance, because it's only the amplitude. The distance affects only the amplitude and not the phase of the waveform. Since the phase of the waveform also affects the intrinsic parameters, we can measure the intrinsic parameters from the phase, and from the extrinsic, from this amplitude and on all the other parameters that we have obtained, we can then estimate. So for example, if you now you know all the intrinsic parameters, like the intrinsic masses of the system, you can say, okay, these are the masses. If I put this binary at a distance of 100 megaparsecs, what is the amplitude of the strain going to be? And you can calculate that number. But you see not that number, but a different number. And this tells you, because this amplitude falls off as 1 over distance, this tells you how far the source should be, in order that the amplitude is not what it would be if the source were at 100 megaparsecs, but it is whatever it is. Yeah. A bit better, or so the observed strain amplitude is dependent on the distance, and you know that if you place the objects with these intrinsic parameters at a certain distance, what the expected strain should be. But you observe a certain strain. From this you can infer what distance this object is at. For example, if you take the intrinsic parameters and then you do not know the distance. You say, okay, maybe this object is at 100 megaparsecs. You place this object at 100 megaparsecs, and then you calculate the strain, and you see that the strain is some 4 into 10 to the minus 21. The strain at some particular frequency or some particular time is 4 into 10 to the minus 21, but your observed strain is only 2 into 10 to the minus 21, then this would tell you that this object is not at a distance of 100 megaparsecs, but must be farther away, since you see only half the strain. So this has to be at 200 megaparsecs instead. Yeah, but for supernova, I mean, with supernova, exactly. But then to go to the expected amplitude, you need to put in some. Astrophysics where there are uncertainties, and which are also calibrated by observing nearby supernova. So that's how you use the standard. That's how you use the distance ladder to calibrate the supernovae first, and then use them as standard candles, right? Here, such a calibration is not necessary, because the phasing comes very directly out of some GR calculations and some NR simulations. Okay, that is one of the main differences here. Okay. Other questions? I'll show you some So one slide about how the data analysis works. So in the data analysis, there are a few steps. So the first step that goes on is the searches. So this is a mock gravitational wave data, and this is a template that we are searching with. And so we actually search for the signal in the data, and if a certain signal is present in the data, we get some kind of a peak in this cross correlation function, and we repeat this search with a number of different templates so that we are sensitive to all kinds of so that we are sensitive to most kinds of systems. This happens very fast. I mean, almost as soon as the detector data is coming in. Now, there is a more rigorous step. Once you're done with the searches, these searches are just to indicate to you which parts of the data are interesting. This part, and they do not really tell you a lot about the system. They do not tell you the exact masses. They tell you almost nothing about the spin components. So for that, you need to do something called parameter estimation, where you do a more rigorous analysis and you try to come up with all these, you try to obtain estimates of all these parameters that I mentioned, 15 or 17. And these parameter estimation also, there are various ways of doing it. There are quick and dirty ways of doing it, and there are rigorous and accurate ways of doing it, and both of these are important because in the end you need to know very precisely what these parameters would be if you want to go ahead and study populations, or if you want to go ahead and see if these things are consistent with generativity. So you have these so-called high latency. High latency means an analysis that takes a long time. So they are accurate and they take a long time. So for that you have high latency parameter estimation. What is also very important for astrophysics is this low latency parameter estimation. So you try to do things as quickly as possible to get an estimate of what are the rough masses, which part of the sky can this be coming from. So if you know to a very rough accuracy which part of the sky these things can be coming from, then you can go ahead and point telescopes at that part of the sky to see if there is a counterpart associated with this. So this low latency dirty parameter estimation is also important in that regard. Let's see, this is for later. Yeah. So the sky localization comes a bit from the fact that the various detectors see the different signals at different times. So that gives you, the triangulation gives you a very basic estimate of the sky localization. Then the different what happens is because you do not know these angles, the distance is not very accurately determined, but there is some kind of a spread in the distance. What happens is instead of getting a very sharp distance, you get the distance correlated with something, with the inclination angle, because this is also an important thing that's going to be important for us. Even to the leading order, the amplitude has this dependence on distance as well as the inclination angle. This one is a cosine 1 plus cosine squared iota. One of them is the cosine iota, but it still depends on the angle, and it's not very easy to measure it. So very often, if we see a estimate of the parameters, these are the contours of the probability distribution, which I'm going to talk about later a bit more. They depend, if this is the distance and the inclination, then you would not see, instead of seeing something very sharp and well localized and not correlated like this, we see instead of something like this, we see something like a banana, and this indicates that these parameters are correlated. And I wrote all the leading order waveforms. If I write the full waveforms, then almost every parameter is correlated with almost every other parameter. And it's not every other parameter, but to a large extent, there are correlations among various parameters. Okay. I'm running out of time, so how much? I have 2 more lectures, but would you suggest I postpone things until evening? 5 minutes. Okay. In 5 minutes, let me answer the question that someone asked: why is this redshift sitting here, and that I didn't talk about. So, for gravitational waves, as I mentioned, this leading order amplitude depends on the mass. I didn't say what mass. I said it's a total mass, but I didn't say it's the total mass. It's the total mass in which coordinates. So it's the total mass in which coordinates? It's the total mass in the coordinates of the system that's emitting these waves. So this is the total mass of the system that is out there. If we observe the system over here, then how is that total mass going to be affected? What mass are we going to see because the system is over there? How is this is because the system is at a large distance where there is a cosmological redshift. Let's say that the cosmological redshift of the system is Z. Let's erase this sector. This is not very important for us. So let's introduce the cosmological redshift Z. So this is one more parameter. Let's really see how this affects things now. How is it going to affect the mass of cosmological redshift? How does redshift affect anything? How is the redshift going to affect a certain time interval t? T would go to 1 plus z times t. So all times would go to 1 plus z times. All frequencies would go to any frequency over 1 plus z. And in these dimensionless units, mass has the same units of time. Mass has the same dimensions as time. I mean, we can go and also check that. Maybe you can do it as a short exercise during the break. So this mass times frequency is actually a dimensionless combination. So a mass is going to go to 1 plus z times the same mass. If you take this object and place it at a distance so far away that it gets a cosmological redshift, then instead of seeing the mass m, you would see the mass 1 plus z times m. And this quantity has been defined as the redshifted mass on these slides over here. So from this gravitational wave phase, alone, we cannot really say whether it's a redshifted, whether it's a object of total mass 60 at z equal to 1, or is it 60 times 2 is 120, so, or it's the object of total mass. What at z equal to 2, what should this be? 60 times 2 is 120, and 40 times 3 is 120. So from the gravitational wave phase alone, we cannot say whether the total mass is 60 and the object is at a redshift of 1, or if the total mass is 40 and the object is at redshift of 2, this would give us the same phase. Okay? However, the amplitude is going to be different, because the amplitude is going to fall off as 1 over, and the amplitude is going to depend on the distance as well. And that is going to be weaker, much weaker for this system than for the other system. Okay, this brings us to a point where we can stop. I was about 3/4 through the stuff that I wanted to cover in this lecture, but I'll begin the next lecture talking about cosmology, and then we'll go over to gravitational wave cosmology. Thank you for your attention, and I can take some questions if you still have. If not, feel free to ask questions during the break, and we'll come back and discuss gravitational wave cosmology in the afternoon.